So I think the coolest effect is our second of our two things that we're going to look at in dealing with sound, and that's Doppler effect. And Doppler effect I think is cool because it actually deals with all waves, not just sound waves, but all waves. The first time you normally see it, like in this case, is probably going to be with sound, but it actually does work for light waves and other types of waves as well. So let's see what this looks like. So up until now, our discussion has all assumed that our mass, or our object that's producing the sound, our source, and the object that's observing it, we call it our observer, are both not moving. We ask a question, or ask actually two questions. What happens if we move the object that produces it? What happens if we move our source? And what happens if we move our observer? So let's think about it for a minute. If we do this, we will see that the frequency will change. The frequency that we hear, what determines the pitch of the sound. So the note A, if you know music, A is one of the octaves of A, is tuned to 440 hertz. Well, if the source or the observer are moving, that value will actually change, or what we'll observe will be a change, will be a value different than 440. So a good example of this is if we take a loudspeaker and run towards it, then the frequency will change, and it'll change because we're going to hit the maximas, the compressions, and the minimas, these compression waves, we're going to hit them at a faster rate. And frequency is determined, the observed frequency is determined by how fast we hit maximums and minimums. So if we're running at the speaker, we encounter these waves quicker. So there's a little diagram of showing. So imagine that we're here and the wave is coming at us. And if we run towards it, we hit these peaks. These peaks were traveling at a certain rate, but we hit them faster. So what happens is it looks like we're stationary, but have a higher frequency, or these peaks look like they're closer together for us. So I'm not going to go through the derivation of this, but we're going to give you the equation for it. Before we do that, there's actually the other case of it. So this is what happens if the observer is moving. There's a possibility that the source, what's producing these waves, can move as well. So in this case, our source, right in the middle, right here, is 0. It's not moving at all. But if we actually look at it and we see if the source starts to move, that each of these waves will be created at the center of the source, but that source is moving, so as this happens, the waves on the front side get compressed because the compressions become closer to each other. So imagine our speakers compressing the sound, or compressing the air. If we're moving that speaker as it's trying to compress the sound, then the stuff at the front side of it is going to be closer together, and the compressions at the back from compression to the next compression are going to be further apart. So we're going to change the frequency in both ways. So we use the Doppler effect. This is what's described as the Doppler effect, and it's given by this equation. It says that V, our velocity of the sound in air, or the velocity of our wave, plus the velocity of the observer, divided by, again, the velocity of our wave minus the velocity of our source. So when I say the velocity of the wave, I mean how fast does the wave propagate through the medium. If we're in air, that's around 340 meters per second. So if we're running at 340 meters per second and we have an observer, like we had up in this case, moving towards the source, then this velocity is the velocity of the person. If our source moves, then we have to include the value of our source. And then we measure the standing frequency of our value. So in the case of this loudspeaker, with 343 meters per second, because that's what the speed of sound is in air, I said we were using A440 for it, and if we're running towards it, this number is going to be a larger number. So if our loudspeaker is stationary, then 340 plus the velocity of the observer is actually a larger number, and we'll see the frequency get larger. So if you've ever been on a street corner when an ambulance or fire truck goes by, you'll hear the noise sound like it's higher and then drop as it goes by. And that's actually really because of this sign that we associate with it. If the observer is going towards the source, or if the source is going towards the observer, then we consider those to be positive values. This negative sign and this positive sign are still there, but do we add in an extra negative or a positive? Depends on if we're traveling towards the source, if they're traveling towards each other, or if they're traveling apart from each other. If they're traveling apart, then we get negative values. So if we get a negative value, then the frequency tends to drop. We get lower sounds. So it's kind of a fun bit of physics that goes in. And apparently there's one of the original experiments that was used to observe this was they took a bunch of people that had constant, or had what's called perfect pitch. They could exactly tell on a piano what note was being played without looking at it. And what they did is they put all these people on a railroad car, and they put an orchestra nearby, and they ran the railroad car by the orchestra. And everybody on the railroad car said that the frequency was one note higher than what it actually was. It's kind of an interesting little bit of experimental physics, but I think a really cool effect.